In the United States, Turkish hospitality has a very high reputation, but it has been far exceeded, in my mind, since I've been here. And I would like to thank Chanal for his gracious hospitality and all the meals, for Yasin, who founded the organization, Dini Chavalpar, for Farkun, for, I hope I remember everyone's name, Ahmet, for driving us around, and also for doing all incredible details, Rana, for the organization and attending to all our needs. It's just been absolutely phenomenal. Thank you very much. It's a real honor to have been invited to speak before such a prestigious group of thinkers, and I'm humbled by the invitation. Coincidentally, 100 years ago, in the 1920s, another prestigious group of philosophers and scientists began a series of regular meetings in Vienna, Austria. Scott Davidson referred to them in his lecture. They were known as the Vienna Circle. They focused on the thinking of Ludwig Wittgenstein, for the most part, on his Tractatus Logico-Philosophicus, where he wrote, "The world is the totality of facts and not of things." Several notable figures attended, some more regularly than others, including Carnap, Fiegel, Frank, Gödel, and Quine. Not all of them were official members. And a central activity of their thinking was to talk about the Tractatus. Ironically, Wittgenstein did not approve of their use of his work. The central tenet that grew out of their movement, logical positivism, is known as the verification principle. And in a nutshell, the verification principle says that to be meaningful, a statement must either be empirically verifiable or logically deducible from previously established truths. Philosophers I've talked to have told me that the verification principle is really now a dead issue because it falls under its own weight. It itself can neither be empirically verified nor logically deduced. Yet strains of this thinking persist among many in the scientific community. And that was brought home forcefully to me not too long ago by an email I received from a mathematical acquaintance. Too bad my clicker's not working. So, oh, that's because I'm not using my clicker. Here it is, okay. So he said this. This is the concluding part of his email. "Hey, I heard somewhere that you wrote a book about math and your faith. Having never understood how a rational person can possibly subscribe to the Christian dogma, except for having some strong, overriding, subconscious need, perhaps, I'm curious about it. Although, if it all comes down to faith, well, I've never had any idea what that really means, and I don't think I have any in me, except perhaps in my ability to reason." Then he closes by saying, "By the way, I'm a happy member of the Skeptic Society out of Altadena." Altadena, by the way, is a suburb about 20 miles northeast of Los Angeles. So when the traffic is good, you can get there by car in about a half hour. Of course, that means it usually takes 5 or 6 hours. You'll note that my acquaintance referred to the Christian dogma, but his attitude was really directed against a variety of religions, and especially against theistic religions that espouse a belief in a personal God, such as Judaism, Christianity, and Islam. The attitude expressed in that email is not new, and it's similar to the thinking that prompted George Berkeley, Bishop of Cloyne, Ireland, to write an essay in 1734. The essay was, in part, a detailed criticism of Newton's calculus, and it has the intriguing title, The Analyst, or A Discourse Addressed to an Infidel Mathematician. But the main purpose of his essay was not to criticize Newton's calculus, as many believe. It was to take issue with a movement that was sweeping through the United Kingdom at his time, known as the free-thinking movement. Here's how his essay begins. Though I'm a stranger to your person, yet I am not, sir, a stranger to the reputation you have acquired in that branch of learning which hath been your peculiar study, nor to the authority that you, therefore, assume in things foreign to your profession, nor to the abuse that you, and too many more of like character, are known to make of such undue authority, to the misleading of unwary persons in matters of the highest concernment, and whereof your mathematical knowledge can by no means qualify you to be a competent judge. So you see, Berkeley is annoyed at a mathematician who is evidently using his scientific authority as a means for assuming equal authority in religion, that is, in the matters of highest concernment. And what's worse, according to Berkeley, he's using that unwarranted authority to mislead others, presumably by steering them away from a belief in God. Who is this infidel mathematician? Contrary to the belief of many, it was certainly not Isaac Newton, because in his essay, Berkeley criticizes those who admire Newton for his science, but deride him for his religion. The best guess is that it was from someone else, by Edmund Halley, the atheist, discoverer of Halley's Comet. And the reason for that is mostly attributed to a biography by Joseph Stock, who writes when the story, according to Stock, is that Berkeley encouraged Joseph Addison, a member of Berkeley's parish, to visit Samuel Garth, a London physician who is desperately ill. He was trying to persuade Garth to confess Jesus Christ as his Lord and Savior. Garth's reply was this: "Surely, Addison, I have good reason not to believe those trifles, since my friend Dr. Halley, who has dealt so much in demonstration, has assured me that the doctrines of Christianity are incomprehensible and the religion itself an impostor." For various reasons, I think that that's probably not the 100% story that was behind this, because this event occurred in 1719, and Berkeley was in Italy at the time. The essay that Berkeley wrote was in 1734, and the gap of 15 years is considerable. What I think more likely is the conversation maybe took place, and maybe Berkeley heard about it somehow, but more likely the essay was prompted by a caustic remark that Edmund Halley made in response to a book that Berkeley published in 1732, just 2 years before he wrote The Analyst. What was that book, and what was the thinking? Well, you can see what the book was by a subtitle of Berkeley's essay. He identifies himself as the author of The Minute Philosopher, and that was his book. The Minute Philosopher was a longer title, actually Alciphron, or The Minute Philosopher, in 7 dialogues concerning an apology for the Christian religion against those who are called free thinkers. Now, according to Alciphron is an ancient Greek sophist. He's teamed up with an associate of his called Lysicles and argue for faith against Euphranor and Crito. I think I said that backwards. Alciphron was the one against faith. Euphranor and Crito were arguing for faith. So Crito says this in the dialogue: "The modern free thinkers are the very same with those Cicero called minute philosophers, which name admirably suits them. They begin a sort of sect which diminish all the valuable things, the thoughts, views, and hopes of man. All the knowledge, notions, and theories of the mind they reduce to sense. Human nature they contract and degrade to a narrow, low standard of animal life and assign us only a small pittance of time instead of immortality. You can see similarities of this with logical positivism. In fact, the free thinkers, with their emphasis on empirical verification, represented an early version of logical positivism. No freethinker would have room in a belief system for paradox, mystery, or ambiguity. Instead, they focused on clear ideas and charged religious people with having obscure ideas. Rationality versus superstition, consensus versus disputes. So that was the ethos that Berkeley was fighting about, and you can see what was going on in the United Kingdom at the time, actually an extended period of time, by looking at tracts that came out during the day, just by reading the titles. In 1696, Christianity Not Mysterious, a treatise showing there is nothing in the gospel contrary to reason nor above it, and that no Christian doctrine can properly be called a mystery. Or, closer to Berkeley's time, a discourse concerning reason with regard to religion and divine revelation, wherein it is shown that reason either is or else that it ought to be a sufficient guide in matters of religion. Berkeley took aim at the free-thinking movement in The Analyst, but with a different emphasis. The subtitle shows what that emphasis is, wherein it is examined whether the object, principles, and inferences of the modern analysis, that is, Newton's calculus, are more distinctly conceived or more evidently deduced than religious mysteries and points of faith. So typical of many 18th century works, you can figure out what he's going to say just by the title. Berkeley is going to argue that the free thinkers break their own rules. Calculus, he is going to contend, that it is much more sloppy and much more careless than any of the thinking that is found among religious thinkers. And he drives this point home by quoting from Matthew chapter 7, verse 5, "First cast out the beam out of thine own eye, and then thou shalt be able to see clearly the mote out of thy brother's eye." What irony. But there's the entire title page of Berkeley's Analyst. Really vague and careless thinking by Newton and his followers? Was Berkeley really serious? Yeah, he really was. And with apologies to those of you in the audience that know calculus, and I'm sure there are many, let's just take a look at some of the things that Berkeley talked about. And what does calculus really do? The reason why Newton invented calculus was partly because he wanted to predict the paths of comets. That dovetailed nicely with his laws of motion and theory of gravity. Knowing where a comet would go, represented by the red line there, would be an important part in determining where the planet or object pulling on the comet was. But in order to get that tangent line, the slope of which would be the velocity of the comet, to get a line, you need to have 2 points. And here you have only 1 point. So Newton abstracted a bit, and he said, well, let's get another point some distance from the original one. In this graph, I've labeled it as the point 1, and here's the point on the curve. And Newton said, I'm just going to go an arbitrary distance past 1, and he called that distance O. And so the important thing to keep in mind is that the slope of a line is always the rise divided by the run. The rise depends on the curve, but the run is always the distance O. And Newton's clever idea was to let O get smaller and smaller. And as you see, that line between the 2 points is getting closer and closer to the red tangent line until, poof, it disappears, and you get the slope. But how exactly do you do that? Well, look at a series of calculations here with the equation y equals x squared and you have the points 1 and 1 plus O. It's not necessary to understand all the mathematical details here, but with that equation, you wind up with equations 1, 2, and 3. So you get down to this bit right here, O times 2 plus O over O. You cancel the 2's and you get 2 plus O. And then Newton says, I'm going to expunge the O. And this is the problem for Berkeley. He said equation 1 and equation 2 is fine as long as O is not 0. But if you move from equation 2 to equation 3, that's invalid, because now you're saying that O is 0. But this is exactly what Newton was doing. Listen to him in his own language. This is Newton's book. Whereas O is supposed to be infinitely little, that it may represent the moments of quantities, the terms that are multiplied by them will be nothing in respect to the rest. Therefore, I reject them. Or again, a little later on. This being done, the terms of the third order will be affected by O of one or more dimensions, and therefore may be expunged as infinitely less than the others. Newton's language was an attempt to get around the problem of dividing by 0. And it was really a bad argument for a good cause. Berkeley did not for a minute dispute the correctness of the conclusions of calculus. He thought, though, that the logic was bad. It would almost be like saying, reduce this fraction to lowest terms, 16 over 64. It's 1/4. Now, how do you get that? Well, I'll cancel the 6's. Then I'll expunge them, and then tidy things up a bit. Now, this is sort of just an analogy. It's not a good analogy because this method doesn't work for all types of fractions, whereas Newton's method did work, or at least so it seemed. But what is the logical justification for it? Berkeley says, look, 1 and 2 are fine as long as O is not 0, but 3 is invalid. Here's what Berkeley says in his own words against Newton. I now beg to make a new supposition, contrary to the first supposition, that there is no increment in x, or that O is nothing. And I get an expression obtained in virtue of my first supposition, and which would not be obtained without it. All of which seems a most inconsistent way of arguing, and as such would not be allowed of in divinity. There you see, you're worse than we are. Now, Newton called these ratios that he got the velocity of evanescent increments, the velocity of an evanescent increment. And so Berkeley says this, what are these fluxions? Another term Newton used. The velocities of evanescent increments? And what are these same evanescent increments? They are neither finite quantities, nor quantities infinitely small, nor yet nothing. And here's my favorite line in the essay. May we not call them the ghosts of departed quantities. You might know that Berkeley was an empirical idealist. That is, he did not believe in the existence of a material world. And many think that he wrote this, had this criticism precisely because believing in something that was so small that you couldn't see or touch would yet somehow exist. In fact, I had a year appointment at Oxford University, and Berkeley spent his last years at Harris Manchester College, and his main mantra, as you know, is esse est percipi, to be is to be perceived. This reveals classic British humor. I didn't want to show you the plaque. It's the blue one right in the middle, but I'll have a close-up of it. Bishop George Berkeley, philosopher, is perceived to have lived and died here. Now, I think it could have also been said, Bishop George Berkeley, mathematician, because his first publication was really in mathematics. And contrary to those who think that his criticism of Newton stemmed from his empirical idealism, that might have been part of it, I think it is mostly due to a philosophical view he held in high regard that required you to be able to conceive an idea about which you are speaking. In his treatise concerning human understanding, the main reason why he rejects John Locke's notion of primary and secondary qualities such as extension and number, and secondary qualities such as color or taste. The reason he rejected that is because he couldn't conceive of the secondary qualities without the primary qualities. But regardless of his underlying motivation, the fact is that his criticism stuck. And here's some of the look at some of the comments on Berkeley's essay that span time. Bishop Berkeley's ingenious criticism in The Analyst remain to this day unanswered. The fact is, Newton himself had no knowledge of the true nature of his method of prime and ultimate ratios. This is almost 100 years later after Berkeley's essay, and the logic of calculus was still in disarray. It wasn't until Augustin Cauchy, maybe much later than that, late 1800s, finally firmed up the theory with limits. In 1992, a philosopher of science who did his dissertation on Berkeley, Newton's procedure here is utterly mysterious, talking about Newton's methods in his publications. So let's back up before I go to the next slide. These were the criticisms. They accepted the criticisms and were scrambling around, and they kept persisting. Why? Because Newton's methods worked. So they believed that something would work. We're going to resolve this issue somehow. In other words, whether they acknowledged it or not, the practice of mathematics for the followers of Newton required faith. But is faith required for the practice of mathematics today? Let's look at what happened since Newton. The criticisms of Berkeley revealed what was needed: an axiomatic system that would describe the mathematical continuum of space and without depending on intuitions of space and time. And what do I mean by an axiomatic system? Well, the axiomatic system is just how mathematicians work. It was a paradigm set in motion in 300 BC by Euclid. Begin with indisputable truths that are worthy of belief. In fact, the word axiom comes from the Greek word axioma, which means worthy. So you believe these things because they're just self-evident and worthy. In the Bible, in Revelation chapter 4, the word axios is used to describe God who is worthy of glory, honor, and power. So we have this fundamental system. We're going to begin with axioms, and then use the rules of reasoning and logical deduction to build up your whole mathematical edifice. The logician Gottlob Frege was about to take a big step in the direction of axiomatizing mathematics with the publication of his work Grundgesetze der Arithmetik, which translates the basic laws or the foundations of arithmetic. And it was a very monumental volume. Unfortunately, just as the edition was in press, about to be published, he got a very disturbing letter from Bertrand Russell. His work, Frege's work, built up all of arithmetic just from 5 axioms, and Russell said, "I've got bad news for you. Your 5th axiom is in conflict with the other 4. In other words, Frege's whole system was inconsistent. This was very upsetting to Frege. It was too late to stop production, so he desperately tried to patch things up, and in an appendix inserted a modified 5th axiom that he thought would resolve the issue. He was also open about the situation. He says, "Hardly anything more unfortunate can befall a scientific writer than to have one of the foundations of his edifice shaken after the work is finished." This was the position I was placed in by a letter of Mr. Bertrand Russell just when the printing of this volume was nearing completion. Unfortunately, it was subsequently shown that Frege's fix didn't work either. It was also inconsistent with the other 4 axioms. But the work to ground mathematics on a logical, firm foundation went on. Bertrand Russell and Alfred North Whitehead, in a series of publications culminating in 1925 to 27, published Principia Mathematica, a highly technical work on logic, which, after several pages of which they say, from this proposition it will follow, when arithmetical addition has been defined, that 1 + 1 = 2. So you have all this amazing logical work leading up to that. And then, around the same time, the logicians Zermelo and Frankel developed a system of axioms. Depending on its formulation, it amounts to about 10 axioms. It's called ZFC for short, Zermelo, Frankel. C stands for the axiom of choice. And it is the basis today of pretty much all of mathematics, those 10 axioms. David Hilbert was impressed by this, and in 1930, he made a statement. He was founder of the School of Formalism, and he said, we're going to make mathematics a mechanical affair. Now we've got these axioms in place, we'll be able to create machinery that will just crank out theorems. The axioms themselves were meaningless strings of symbols, but they derived their meaning by their internal use within the system. So you see the influence of Wittgenstein here again, because for Hilbert, meaning was determined by use, its use within the system. And here's his assessment. In 1930, the fundamental idea of my proof theory is none other than to describe the activity of our understanding, to make a protocol of the rules according to which our thinking actually proceeds. Already at this time, I would like to assert what the final outcome will be. Mathematics is a presuppositionalist science. To found it, I do not need God or the assumption of a special faculty of our understanding. Now, this person was mentioned already, and many of you know this story. Just 1 year after this statement, the logician Kurt Gödel, I've showed his wedding picture here, but this happened in 1931, dealt a fatal blow to Hilbert's program. Not many people in the US know of Gödel, so here's a picture of him with someone that everyone does know at Princeton's Advanced Institute, Albert Einstein. Here's the classic mid-career picture of Gödel. And in 1931, just 1 year after Hilbert's very bold and dogmatic statement, he proved a series of theorems that dealt a blow to his program. The first was this: if PM, the system of Russell and Whitehead, if it's consistent, it contains true propositions that can't be proven to be true, and it contains false propositions that can't be proven to be false. I can't resist but showing the symbolism that he used in the construction of his theorem. These are all logical symbols, but generally they have the meaning this. This first part here is if there exists a proposition Y, such that there is no sequence of deductions capable of demonstrating it, then there is no sequence of deductions X that can demonstrate the proposition this. It's a very technical meaning, but that was the proposition. So that really carries the meaning, if there's something that can't be demonstrated, that means the system is consistent, because in an inconsistent system, everything can be demonstrated. If there is something that can't be, then this statement can't be demonstrated. All right, so there's true propositions or false propositions that you can't prove. He also proved this: if PM, Principia Mathematica, is consistent, it cannot be proven to be consistent. And even worse, his axiomatics, Gödel showed that my theory works on any axiomatic system that you can possibly create that's powerful enough to do addition and multiplication. In other words, ZFC suffers from the same dilemma. If it is consistent, it can't be proven to be consistent. Well, this is bad news. Ask a typical mathematician, do you believe that ZFC is consistent? And the answer you will get is yes. And if you ask that person, why do you believe the work you're doing? You think this would throw us into a tizzy, right? But we go on, as mathematicians, happily proving theorems on the belief that ZFC is consistent. Why do we think that? I've asked several, and the answers go something like this. Well, look, I know that I cannot prove that ZFC is consistent, but I've got good reasons to believe it is. No contradiction has been found now in over 100 years. The results of mathematics are very powerful and work in the real world. So these outcomes are the evidence of something I hope for, a consistency. They're the assurance of something that I don't see or know I can't see, a proof for the consistency. The evidence of something hoped for. the assurance of something not seen. In many theistic traditions, that's an apt description of faith. In fact, in the book of Hebrews, it's almost identical, where it says, "Now faith is the assurance of things hoped for, the conviction of things not seen, for by it people of old received their commendation. By faith, we understand that the universe was created by the word of God, so that what is seen was not made out of things that are visible." So yes, today, faith is required for mathematics. I want to spend just a little bit of time asking the reverse question. Is mathematics required for faith? Well, of course not, but I'd like to argue that it can be helpful in producing a fuller, deeper faith. And I'll try to illustrate this with some examples. The first is something that was alluded to before, and I'm sure which many of you know. In mathematics, there are actually different sizes of infinity. You can have one collection of numbers that is infinite and another collection that's infinite, and yet the second collection is bigger than the first. Now, I would contend that once a student sees the proof of that result, their statement and their thinking about God being infinitely wise, infinitely powerful, or infinitely good carries on a deeper, richer meaning, one that would not be possible without seeing that proof. And there's another interesting conundrum that arises. I would maintain that mathematics can be helpful in dealing with paradoxes when they come up in faith. Paradoxes or mysteries. This is the graph of the line y equals 1 over x. If you rotate it about the x-axis, you get a megaphone. And then stretch it out to infinity, you get something in the guild known as Gabriel's horn. You can prove mathematically that the volume inside this object is finite. In fact, it equals pi. You can also prove that the surface area is infinite. And as one student asked me once, wait a minute, if the volume is finite, you can fill it with paint. But if the surface area is infinite, you can't paint it. You can fill it with paint, but you can't paint the surface. As it is with faith, I think this is a paradox, but I think it's one that's very easily resolved. Here's something that's not quite so easy. It's known as the Barnard-Tarski paradox. Using the axioms of ZFC, Barnard and Tarski were able to show that it's possible to take a sphere and decompose it into only 5 sections, then without twisting or bending or distorting those sections in any way, the sphere can be reassembled into 2 spheres of identical volume. As with faith, I think this is a paradox, and one that's not quite so easy to resolve. And here's an irrational conundrum. We mentioned sizes of infinity. The 2 sizes I was thinking of are the rational numbers, which can be represented by fractions, and irrational numbers, like the square root of 2 and pi, that you can't write as a fraction. Now, here's a series of statements. Between any 2 rational numbers on the number line, there is an irrational number. And between any 2 rational numbers, there's an irrational on the number line. Between any 2 irrational numbers, there's a rational number. Yet there are more irrationals than rationals, though there are infinitely many of both. By the way, there is an infinite collection of sizes of infinity that Georg Cantor showed. Now, I'd like to suggest that if things can get this convoluted in a logically precise, carefully defined world such as mathematics, it shouldn't surprise us when we find paradoxes and mysteries in our faith. If I've asked several mathematicians, what do you think about that? Does that really make sense to you? And what they say is, well, that's just the way things are with infinity. Indeed, that's just the way things are with infinity, with the mysteries of mathematics and the mysteries of our faith. So, this reminds me of a statement that the Apostle Paul made in 1 Corinthians chapter 13. For now we see in a glass darkly, but then face to face. Now I know in part, but then I will know fully, just as I've been fully known. In other words, these paradoxes help me live more freely with paradoxes, mysteries, ambiguities in my faith. Let's let Bishop Barclay have the penultimate word. He closes his essay with a series of rhetorical queries. 4 of the final ones are this, and now he's writing to this infidel mathematician, presumably Edmund Halley, whether it not be less reasonable to admit points above reason than contrary to reason. One of the points in Al-Kifron that I talked to you earlier was in the early dialogues, revelation is by almost by nature has to be foreign from a human experience, just by the virtue of the fact of its being revelation. So we shouldn't expect to see something that's paradoxical about it. Whether mysteries may not with better right be allowed of in divine faith than in human science. Whether mathematicians, as cry out against mysteries, have ever examined their own principles. These are all rhetorical. In other words, Barclay says, you have not done this. Whether mathematicians who are so delicate in religious points are strictly scrupulous in their own science. Whether they do not submit to authority, take things upon trust, and believe points inconceivable. If you go to any university in the world, pick out a random mathematician, ask him or her to state the 10 axioms of ZFC upon which all his or her work is based, I will guarantee you, unless that person works in the area of logic, he or she will not be able to list the axioms. And if you go to any mathematician in the world and ask whether he or she believes some of the great results that have been proved in the last 50 years, such as Andrew Wiles' proof of Fermat's last theorem, I guarantee the answer will be yes, I believe that that is true, that Wiles' proof is true. If you ask that person, have you read through the proof? The answer will be no. In fact, I would estimate that there are fewer than 500 mathematicians in the world even capable of understanding Wiles' proof. Yet we all believe that it is true. Whether they do not submit to authority, take things upon trust, and believe points inconceivable, whether they not have their mysteries and what's more, their repugnancies and contradictions. I don't know about that part, but at least that's what Barclay thought. So let's circle back in conclusion to that email I received from my free-thinking friend, where he said, I don't understand how a rational person can subscribe to the Christian dogma. How did I respond? Well, I said, let's get together for breakfast. And when we met, I reviewed this history in fact, that was the occasion, my coming up for this lecture. I reviewed the history of this that I just shared with you. And during our conversation, he allowed for some points, but remains a skeptic, although I hope more respectful of people who have religious beliefs and more aware of faith commitments that he must make. In fact, when you think about it, a respectful attitude is almost demanded of every mathematician towards people of faith. There's a little bit of disciplinary arrogance in here, but I think in some sense mathematics is unique in that regard in terms of forcing people to have a humble and appreciative attitude of people of faith. As one wit commented, if science deals with what can be proved and religion deals with what cannot be proved, then mathematics is the only science that can prove itself to be a religion. Thank you very much for your kind attention.
Soruları alabiliriz. Arkada.
Can I say before questions, again, I want to thank the translator, because it is just enormous work to be able to concentrate for so long translating into another language. And thank you all for staying so late on a rainy Sunday when there's some sort of football match going on that you could be watching.
Firstly, thank you so much for your presentation. My question is about the usability of methods that are not empirical but logical in order to investigate and discover the God and some things about metaphysics. Our religion teacher, Ahmet Hamdi Ayan, has mentioned us...
Where is the person asking
All the
the
way
question?
back, on the right.
Oh, okay, yeah.
Here. Our religion teacher, Ahmet Hamdi Ayan, has mentioned 3 years ago to us about the Descartes' quote of I think, therefore I am, and the logical argumentation chain as a source of this principle of Descartes, which is I can't be suspicious about me being skeptical, me being suspicious, so I exist. The extent of what I think is wider than what I can achieve or I can do. So it's impossible that I have created myself, and there should be a creator, a force, which has created and limited me, and which is as unlimited, at least as unlimited as I can imagine. So he described the God by this way. And my question about this is, according to this chain of argumentation, is the main source of human ability to manipulate the physical limitations to the direction of good or to the direction of bad, the free will, the source of it, and according to that principle, is the free will the only thing which makes the human more precious than the other species or all the other objects? Thank you.
Maybe I need to ask for some clarification. You began by quoting Descartes, I think, therefore I am. But your question at the end seems nothing to do with Descartes. Can you repeat that last bit of your question?
Actually, I tried to say that according to the Descartes' quote and the argumentation change which led to that quote, it states the principle that God as a creator limited the person with the physical limitations, with the physical rules, and the free will which can manipulate these physical rules in the direction of good or bad, does it come from free will? And according to that principle, can free will be the main essence which makes humans so precious?
I think what makes humans precious in Islam, Christianity, and Judaism is that they are made in God's image. And God values that, and just intrinsically, being made in God's image is valuable. Free will is a complicated issue. I believe that humans have free will. You might even say, though, if not, being made in God's image is ipso facto a criterion for being valuable. Descartes, as you know, was a rationalist, so he began by proving things. I think, therefore, I am sort of gets shattered, I think, in the British empirical tradition of Locke, Berkeley, Hume, that I say that Locke has sort of a metaphysical atomism view of nature, that Berkeley takes sort of to one logical step and Hume takes to another logical step. I don't quite subscribe to that metaphysic, But a metaphysical view about human value is sort of behind your question. And for me, it goes back to being an image bearer of God that gives me value. And I think that entails freedom, but I don't think freedom would necessarily be required for being of value. I don't know, did I answer your question? Or?
Of course.
Okay.
Thank you.
Thank you.
Thank you very much for the presentation. In physics, there was a progression from, Newtonian physics to Einstein's findings later with the theory of relativity. Do you think? What are your thoughts on, in mathematics, a similar trajectory being followed as far as the currently accepted system of axioms are concerned? And in the future, what are your thoughts about creating a revised set of axioms that can be proven to be consistent? And how do you think this possibility affects that faith factor among mathematicians?
Yeah, good. Thank you for that question. Good question. First of all, Gödel's theorem shows that no matter how many axioms you'll have, if it is a consistent system, you will not be able to have a complete system, something that answers all your questions. So these two different sizes of infinity, for instance, the infinity for the rational numbers and the infinity for the real numbers, Georg Cantor, who first demonstrated that, postulated that there would be no level of infinity between them. And he thought he had a proof, turned out it was wrong. Then he thought he had a proof he was wrong, turned out that was wrong. And when he died, the matter was unsettled. Coincidentally, in 1940, Gödel proved that if you take Cantor's stipulation that there's no level of infinity between these two, and add that as an axiom, if the original set is consistent, so is the new one. But then in 1960, Paul Cohen at Stanford University showed that if you assume that the denial of what Cantor said is true, and you add that to your system, that is, there are levels of infinity between, you still get a consistent system. So that it's just independent. Now, a question that would be good to ask is, all right, you can't prove with the current ZFC whether there is a level of infinity between these two. Is there or is there not? Well, if you think there is, you'd add that axiom in. If you think there isn't, you would just add that axiom in. You might ask, does God know? And your answer to that question will depend on your view of mathematical objects. Whether there are human constructions, in which case you would say, no, God doesn't know because it's up to humans to create the axioms. Or, yes, God does know because there's a reality to mathematics that's independent of human thought. I hope I touched on your question somewhat, at least. Okay.
Okay, so thanks again for Russell for the talk and for all the other panelists.